So this is the Waves homework booklet, question 12. We've got ultrasound waves being used to produce the image of a fetus inside the womb. Explain what is meant by the frequency, simply the number of oscillations per unit time. You could give that as the number of wave cycles passing a point in a second or in a unit time. Ultrasound is an longitudinal wave. Describe what is meant by a longitudinal wave. We've got to have the oscillation, not just the movement or the displacement, but the oscillation of the medium, of the particles, is parallel to the direction that the wave travels. Instead of the direction the wave travels, we could have the direction of wave propagation or the direction energy is transferred. So again, it's about being really clear what the two directions are. We've got the direction of oscillation and we've got the direction of energy transfer, of propagation of the wave, of the direction the wave's travelling. And the key thing is to say that those two things are perpendicular. In order to produce an image with sufficient detail, the wavelength of ultrasound must be 0.5 millimeters, 0.50 millimeters. The speed is 1540 meters per second. Calculate the frequency of the ultrasound of this wavelength and give your answer to an appropriate number of significant figures. Well, it's basically a C equals F lambda question, so F is C upon lambda, 1540 over 0.5 times 10 to the minus 3. We get that value. Now, the question did say give your answer to an appropriate number of significant figures. Yes, we've got 3 significant figures in the 1540, but we've only got 2 in the 0.5 millimeters. Therefore, you should only be giving that answer to 2 significant figures, 3.1 times 10 to the minus 6. It's okay to give it as 3,100,000, but it's not utterly clear how many significant figures that is, because we don't know whether all these zeros are significant or not. The advantage of writing it in standard form is we can simply stop after the number of figures that we consider to be significant. The correct number here is 2. We then have got another question, just like we had back in question 10, where ultimately what it's asking us to do is to spot that we've got stationary waves forming and to therefore give some explanation on the basis of that. So we've got a continuous ultrasound wave of constant frequency being reflected from the solid surface and it returns in the direction it came from. So there's my transmitter and there's my reflected wave. Assuming there's no significant loss in amplitude upon reflection, describe and explain the effect of the waves on the particle in the medium in this area between the transmitter and the solid surface. So we're going to have waves travelling in 2 different directions. That's going to form a stationary wave. The significance why they've told us that there's no significant loss of amplitude is it means that the antinodes will have twice the amplitude of the individual waves and the nodes will have 0 amplitude. If your 2 waves are significantly different sizes, you can still arguably have a stationary wave. It's just your nodes won't be 0, your antinodes won't be twice the size. This occasion it looks like it was easier to go with the explanation before the description of what the particle's doing. So the explanation is that we've formed a stationary wave because we've got 2 waves of the same frequency travelling in opposite directions superposing. Constructive interference producing antinodes and destructive producing nodes. So in terms of the description, we're not just after a description of a stationary wave, but remember the effect the waves have on the particles. So we're after describing the motion of the particles in that stationary wave. There are a lot of things that you could say here. You have to have something from each of the 2. Wrong button. You have to have something from each of the 2 lists here. But for the description, we can have particles not moving at the node and particles vibrating with maximum amplitude antinodes. We can have at either side of the nodes the particles are in antiphase with each other. Between the nodes the amplitudes vary and the particles are in phase with each other. And we can also have the fact that we know this is a longitudinal wave, so we can still, because we were asked about the motion of the particles, we have got the particles, the ones that do vibrate, are going to be vibrating parallel to the line between the transmitter and the solid surface. That is parallel to the direction the waves are moving. So that's the Waves homework booklet, question 12.